Okay, so we'll move on with our second talk of today. And our second talk is from Professor Jesus Lizana. Jesus has very interesting background in that he has background in engineering, but also architecture as well, so really quite unique. So Jesus is going to talk to us today about the future of net zero buildings and also the sustainable use of materials in construction. I think there's a contribution here from Professor Barbara Rossi as well. So Jesus leads research on zero carbon space heating and cooling in our Zero Institute, which I'm sure many of you have heard about, and I'm sure you'll hear more about over the day today. And then Barbara leads our Sustainable Metals Research Group within engineering science. So with that, I'm going to hand over to Jesus for our second talk.
Thank you. Well, fantastic. Good afternoon, everyone. Well, I am Jesus Lizana from Spain. As it was said, I have a background in architecture and engineering. I was working in the building industry in different engineering consultancies in Spain. But after that, I decided to join to the academia. I was working in Spain, Lisbon, in Munich, in Edinburgh, Spain again, and now here in Oxford, where I started last year in January 2024 as an associate professor in the Department of Engineering here in Oxford, and also leading member of the leadership team at the Zero Institute, where we try to accelerate the transition to a just and fair zero carbon energy sector. At the Zero Institute, we address research for the core main pillars of the energy system, research on generation, conversion, distribution, storage, and energy use across the four main energy sectors: the power sector, transport sector, the industry sector, and the building sector. In my case, all the initiatives that I'm coordinating inside the Zero Institute are associated to the building sector in order to reach net zero by 2050. How can I describe the situation of the building sector in one slide? I will try. Imagine that you're going to buy a new car, and suddenly you discover the following. The delivery date is delayed, so you will need to wait 6 months more to get your car. The final price is going to be slightly higher than anticipated. You will have to pay 30% more, something that you didn't see coming. You start driving your car, and the fuel consumption per mile is much higher than you anticipated. Unbelievable. There is no way to know if the car is working properly until it breaks down. Will you buy this car? I'm sure no. Welcome to the building sector. Probably the worst sector to decarbonize. We are not even close to the right path to reach net zero by 2050. We even didn't start. So will things improve next year? Sadly, the building sector is responsible for 1/3 of the carbon emissions globally. 27% related to the building operations, what we call the operational carbon, and 10% related to the materials and construction, the embodied carbon. What is the role here of building services engineering in achieving net zero in the building sector? We have a large portfolio of technologies that we can apply in the building sector. Technologies for generation, conversion, storage, distribution, and energy use, for electricity, to provide heat, and to provide cool. It's just about one technology. Is this going to solve the problem? If we need to talk about one technology, probably heat pumps will be the technology that we are all talking about. Why? It's the technology with the highest efficiency, probably the most promising technology for heating and cooling in the building sector. Of course, as an academic institution, we have the role to share the best practices to our students. And this is something that at the Zero Institute we know well, and we are starting. We started last year introducing new courses, new lecture into not only engineering, other MSc programs in engineering and geography, and even planning the field programs and executive education. We also are creating educational resources, educational publications, software and tools in order to promote education, to train the future engineering leaders to net zero. And at the same time, we are motivating students to try to develop innovation in the sector. Now we have 3 fantastic students that are representing the UK team for the European competition on zero carbon data centers, where I hope that they will win. They will submit the proposal in July this year. This is an initiative that we started last year and was globally recognized by the 2 major chartered institutions on building services in engineering. First, the CIFSE, the Chartered Institution of Building Services Engineering, based in the UK, with the CIPS Award 2025 in Learning and Development, and also by ASRAE, the ASRAE Award for Zero Carbon Education, the American Society of Heating, Refrigeration, and Air Conditioning Engineers. But is this enough? Are the best practices in the building sector enough to be net zero? It's just a question of investing, of sharing knowledge, or implementing best practices? Well, in this case, I will use my college, Wolfson College, to help me to try to share what we can achieve with the best practices. But you know, Wolfson College was the first and the major decarbonization project that we have in Oxford, an investment higher than £8 million in order to decarbonize Wolfson Estates, a project that started in 2021. Before going into detail to try to answer this question, what is a net zero building? We have a new standard, and a standard that defines what are the limits and the targets and the requirements that we need to meet in order to align the building sector to the UK net zero strategy. Something interesting about this standard is that we don't need to eliminate carbon emissions. So the concept is to prepare the building to be net zero, a zero carbon ready building. So we need to fully electrify the building, and also we need to limit the energy demand. We may think that this maybe is not enough, but it's going to be very hard. And here you can see in this figure the target. So in the left side, you can see the final energy consumption in kilowatt hours per square meter. These are the color bars. And in the right side, you can see the carbon emissions in kilograms of CO2 equivalent per square meter. The target for a college in Oxford, in the UK, for a student accommodation in this case, is below 100 kilowatts. And there is no target for carbon emissions. Remember this concept about zero carbon ready building. How much is the consumption of a college in Oxford? Do you have any reference value? Of course, lower than 400. Wolfson College, the baseline was slightly close to 350 kilowatt hour per square meter. This is an average across 3 years. 2021, what happened? COVID. So the starting point of the intervention was not there, it was in 2022. And here we selected the 2 best practices in order to decarbonize: building fabric and the best heat pump technology in the market. Building fabric, in this case, this is a brutally silent architecture. Most of the building envelope is glazing, so the best glazing technology in the market, able to reach a U value close to 0.4. And the best heat pump technology, we have a heating capacity of 2.4 megawatts. We were able to electrify using 2 CO2 heat pumps with a total capacity of 700 kilowatts. Do you think that we are close to the target? How many of you think that we are below 150? Come on. Well, 2021, as I said, the COVID, the lockdown, so we had a decrease in the consumption. 2022, we started the decarbonization project. Of course, at that time, we still had gas. Even we finished the decarbonization process in 2023. Was 2024 the reference year where the building was working fully electrified, only with the heat pump, with no more gas? What can you see here? Massive investment, very complex project, best technology, not enough. So the best practices alone will not get us to net zero. So what can we do now? Of course, here is where, as a research institution in the Zero Institute, this is the program that I'm coordinating on zero carbon heating and cooling, where I have research on new materials and technologies to decarbonize heating, to understand how climate change is going to impact heating and cooling demand globally, and at the same time, how to define ultra-low-cost cooling technologies to support climate adaptation. But here, I will focus only on climate change mitigation, on heating decarbonization. This is the hot topic right now in Oxford and in the UK. And this is not a research that I'm doing alone. Research in the last 10 years collaborated with more than 65 international academic and non-academic institutions, and with contributions from many of the colleges working with me at the Zero Institute are here today. So briefly, the three most exciting projects. I am sure that you all have a home, maybe planning to buy a heat pump. I hope that these three ideas, radical ideas, can inspire you. The first one is a hybrid indoor design conditions. This is a Marie Curie project. We started this in a Marie Curie project 2 years ago. The second one is the optimal sizing or control of heating systems. This is a new project I started last year, a EPSRC project, and a better auxiliary system for heating systems. I am going to them. The first one is about this key message. Thermal comfort is not about temperature. We traditionally address heating by modifying the drivable temperature. It's the temperature that we see in a thermostat. But we have 6 thermal comfort variables that we can use to address thermal comfort: humidity, air speed, air temperature, radiant mean temperature, and 2 personal variables: the metabolic rate, according to the activity that we are performing, and the clothing insulation, the layers that we are wearing. What is the opportunity? The opportunity is that for every degree Celsius that we decrease the thermostat, we can save between 5 and 10% of heating, energy demand for heating. This is huge. It's a huge opportunity. And here, we need to talk about psychrometry. So psychrometry is the part of engineering that studies the physical and thermal properties of the moist air. It's a combination of dry air and water vapor. And the psychrometric chart is the tool that we use for sizing and calculating heating, ventilation, and air conditioning systems. We can see in the horizontal bar, we can see the drivable temperature, and the relative humidity are these lines going up. So the red point will be associated to the indoor design conditions that we need to meet for our heating system. And the pink area will be the comfort zone, more or less where we may feel comfortable. How do we calculate the heating system, the capacity? We need the outdoor design conditions. So these conditions are related to a percentile of the historical temperature. For Oxford, minus 5.5 degrees Celsius, or minus 3.7 degrees Celsius, according to the percentile that we are using, according to the building typology. Can we do this without sacrificing comfort? This will be super interesting. Why? Because we can reduce the energy demand easily by 30%, and we can reduce the peak load for the heating system. Don't try this at home. It can be very dangerous. This was last year, town hall. Someone provoked a thermostat work trying this. So, this is a joke, but a cabinet member said, clearly someone has lost the temper and thought, right, I am going to solve the problem right now by padlocking the radiator. This can provoke problems and conflict. But at the Zero Institute, we have a solution for this. I will explain. What we can measure can be controlled. So first, we need to understand how we can measure thermal comfort. And we can do it. So we build a device that we can use to measure all the thermal comfort variables. And we can measure thermal comfort using the predicted mean boat index. This is not new. So this is from the 70s. This is an index from +3 to -3, where we can characterize the thermal comfort sensation. So 0 is the neutral zone. The neutral zone is, 0 will be the perfect point. And the neutral zone will go from -0.5 to +0.5. Something interesting is that with this model, we can also predict the percentage of dissatisfied people. So even in the neutral zone, 10% of people will be dissatisfied. We need to remember this. So the second thing, after you measure, you need to inform these people about stop complaining. You need to inform these people that they have the right to complain, but not the right to modify the settings. That's clear. As soon as you understand that you are in the thermal cone, in a neutral zone, then you can start playing with the system. You can move from the traditional approach to address heating to a hybrid approach. In here, in the psychrometric diagram, now we can plot the thermal comfort sensation. And the white area will be the neutral zone. How can we move from the classical approach to a hybrid approach? The secret is using radiant heat. For example, introducing infrared heating. Introducing infrared heating, we can increase the mean radiant temperature, and we can move down the neutral zone, basically reducing the dry bulb temperature at which we feel comfortable. And the opportunity is huge. So where we are right now, understanding that there is a potential benefit if we move the set point temperature from 21 to a lower value. But we need to balance what is the consumption of this radiant heat in order to make sure that there is a net benefit. This is where we are. Do you know why in Spain we have the siestas, the naps, at the hottest hours of the day? It's quite fun. When we sleep, we reduce one of these thermal comfort variables. We reduce the metabolic rate. So reducing the metabolic rate, suddenly we are increasing the thermal comfort zone to a higher temperature. So when we sleep at the temperature that we feel comfortable, suddenly it's 27. So it's not because we are lazy. It's just because we need to reduce the metabolic rate. Remember that. The second project is about understanding this key message. It's time to stop over-engineering systems for managing peak loads. This is super important. After 10 years of experience in the building sector, we can see how energy systems for heating and cooling, they are traditionally oversized by a factor of 1.5 or 2, easily. With gas boilers, this was not a problem. They were cheap. But with heat pumps, this is a huge problem. The price is 10 times higher. So we need to optimize. We need to calculate bien how we design heating systems in buildings. Again, same psychrometric diagrams. You see, I love psychrometry. And here, how many hours in a year do you think that we reach the peak design load? Few, right? How many days in Oxford we have minus 5.5 degrees Celsius? Well, this is the zero institute. In this plot, you can see the heating load duration curve for the zero institute. Basically, how is the distribution of the load in a year, in a heating season in this case. So we can see traditionally for in this building, it's an office building, the percentile to calculate the heating system will be the 99th percentile. And you can see the heating load exceeds 75 kilowatts just for 80 hours a year, in a year. Can you guess how much was the installed capacity? Just 100, just in case. 100 kilowatts. And here, the best practices are always the same. We normally have an auxiliary system that is able to meet 1/3 of the load. Traditionally, it can be a gas boiler, an electric heater, because they are cheaper. And then the main energy system in also, for example, the 2 CO2 heat pumps that we have to reach 700 kilowatts. The most interesting thing is that with the power of digitalization and artificial intelligence, we can change completely this. So we can avoid, even eliminate this worst case scenario of this peak load. And we can run the building in a way that we never meet a load higher than 50 or 60 kilowatts. This is a huge opportunity. It's a huge reduction of the capital cost for the new heating system. This is one example of the curve that we can achieve. How? Digitalization, reducing the set point temperature, increasing the temperature, basically heating the building slightly at night, introducing the smart demand response to try to balance the load. So there are many strategies, and it's just about control. There is no technology that we need to implement, it's just control. Something really interesting, as soon as we reduce the load, we can also reduce the temperature at which we run the heating system. Traditionally, for gas boilers, the temperature was 70 degrees Celsius. For 70 degrees Celsius, of course, we can meet the peak load. But now the peak load is much lower. We can run the system at a lower temperature. If we reduce the temperature, we suddenly increase drastically the efficiency of the heat pump. For a heat pump, the higher is the delta T, the higher is the efficiency. So with this strategy, first, we can reduce drastically the capital cost, and we can increase drastically the energy savings. So it's a huge opportunity. So here in this project, what we are doing is how to start calculating these future heating systems more efficiently in a more sustainable way. This is what we are creating is a software that with a minimum input values and using a physics-based building model, we calibrate the model using a data-driven calibration process using the energy bills. After that, we try to identify the optimal sizing for the heating systems, understanding and comparing all the opportunities that we have to start controlling the building more efficiently. The last key message, investment, the last project is about this key message. Investment in an auxiliary system for just 96 hours a year doesn't make sense. I hope you agree with me here. This is an example of the best practices in a heating system. This is for the TIPSE journal, where we have a heat pump, in this case. I'm not sure if this works. No. We have a heat pump for heating and hot water, and we have this auxiliary system that we can use or not, only when we have this high peak demand. How can we replace this system for another component that we can use more, not only for peak loads? Any suggestions? Where we are working here is high-density heat batteries. The idea here is to start integrating heat batteries in a way that they can help to meet the peak load, but in a way that we can also provide energy flexibility to the network. So a heat battery that we can use to balance the energy demand and supply when we have renewable availability, but at the same time that can help us to the building to meet that peak load. What is the most promising material for this? This is a research that I started 10 years ago during my PhD. And of course, water is the most common material that we find in buildings for whole water storage. That's quite common. We have latent heat storage, thermochemical heat storage. And where we are now is working with solid absorption thermochemical heat storage. This is where we identify the most promising material, because there are many requirements that we need to meet. Remember this, zero carbon heating means low temperature heating. The lower the temperature, the higher is the efficiency. So we need a thermochemical reaction able to charge between 30 degrees Celsius and 45 degrees Celsius, and discharging reaching a temperature close to 50 degrees Celsius. This is low temperature energy storage. But here we are working with sodium acetate-based composite materials that, as you see in the first figure, we can dehydrate. This case is a dehydration-hydration reaction. We eliminate the water content in the first figure, even at 30 degrees Celsius, and in the second figure, by adding water, we can discharge the heat battery. Where we are here now, we published last year the proof of concept of this technology, and we are now focusing on the prototyping and how to start developing this technology. From here, in the building legacy, right now where we are, the operational carbon is responsible for 80% of the carbon emissions in a building. This is the main problem now. This was also where heating and hot water was the highest energy use in the building. But in the future, as soon as we continue decarbonizing, the problem will not be associated to the operational carbon, will be associated to the embodied carbon. The materials and the construction processes that we use to build out, to integrate new interventions into buildings. And here is where I am delighted to introduce the research led by Professor Barbara Rossi, Associate Professor in the Department of Engineering, working as an academic practitioner in the development of sustainable structures and materials for civil engineering. Barbara is fellow of the Institution of Civil Engineers, and here I will briefly explain the research that she's leading. The role of materials. What are the most common materials that are contributing to the embodied carbon in a building? Concrete, steel, plaster, mortar. major contributions are related to this, a narrow selection of material. And here, the strategy is we need to move away from business as usual. As I did previously, I'm going to start with the best exemplars in Oxford. New College Campus, intervention, a project of more than 5,600 square meters in the city center of Oxford, the Gradle quadrangles, where the intervention of the support in the early stages of the decision process from Barbara Rossi, they were able to reduce the embodied carbon by 55%, a massive reduction. How? In three main components: superstructure, and the building facade of the building. The analysis, basically the focus was to perform a parametric analysis of different materials, different integration of materials to meet the requirements that they need for that specific building. And with that analysis, they were able to identify what are the best choices in order to reduce the embodied carbon. And I will explain more in detail here. This is a second example, the Waterford Research Building. This is an intervention on the historic Waterford Hospital site in Oxford. The process is the same. Here they try to perform a life cycle assessment to try to analyze different structural solutions, foundations, and facade options in order to understand what are the key elements that they need to modify or to suggest into the building. And there are four main key messages that I would like to share here today. We cannot analyze every single component of the building individually. So we need an holistic analysis. So we need to analyze superstructure, and the envelope together in order to identify the optimal solution. Why? Basically because in lightweight structures, if we choose for a lightweight structure, they will reduce the amount of material for that single structure, but at the same time, that is going to affect also to the foundation. That's quite obvious. Also, it's not only about the material selection, it's at the same time about the design. So the grid site matters here. So by suggesting a different structural layout for the building, they were able to save 27% of the body carbon for the building. So not only about the material selection, also the structural design here. And when possible, timber-based solutions when possible in order to reduce the embodied carbon, the amount of concrete or steel that we use for the building. For the building envelope, for the facade of the building, what were the key findings from this project? The ratio of glazing is crucial. So the higher is the ratio of glazing in the building, the higher will be the embodied carbon of the facade. So this was quite important. As excessive glazing will increase drastically the embodied carbon of the building. And the second key message is that technical frame solution has the higher impact at glass. So the frame selection is more important than the glass choice in order to reduce the embodied carbon of the openings of a building. The last part where they were working was to how to define alternative binders to concrete, how to reduce the embodied carbon of the concrete that they use for this project. And here, the reduction was massive. They were able to reduce between 34% and 37% of the embodied carbon associated to the building project. Again, are the best practices on embodied carbon enough to net zero? Well, let me tell you the numbers. In a legacy building, the embodied carbon associated to a new building project is higher than 800 kilograms of CO2 equivalent per square meter. With the best practices right now, we move between 400, 650. But with the new standard requires us to reach 50 in 2050. So we are not even close. This is where Barbara Rossi is leading research, about bringing innovation on new composite materials that are able to meet the same durability, the same strength, the same requirements that we need in these materials in order to reduce the amount of material that we need for these requirements and the embodied carbon of these components. And here I will finalize my intervention with three takeaways, key takeaways. Remember, it's not only about the technology of the material. The process, the design process is essential. And we need to move beyond the traditional practices that are holding us back. This is quite crucial. You see, all the innovations here were based on radical innovations about the process. Technologies are the same, but we need to change how we address the problem. The last one, we are behind, but it's not too late to change. This is something that we are promoting in the Zero Institute. We are promoting this with the vision of creating a working group on the future of zero buildings at Oxford. This is an initiative that I'm coordinating, and I hope many of you can join us here, because the idea here is to start working together to support university state services, but at the same time to all the colleges that right now are defining a decarbonization path to be net zero by 2035. Not by 2050, 2035. So the idea is that we can work together, academics and also members of the Oxford community, in order to define not the best practices, the radical innovations that are going to help us to reach net zero. I hope that together we can pave the way towards a sustainable and net zero future at Oxford, and that we can also use that as a way to scale up the radical innovations that we need in the building sector to reach the global target. Thank you very much.